Okay, so we're on greatest common factor, and this is going to be called Euclid's algorithm. So this is an alternative way to find the greatest common factor of something. So I've got the steps over here, but we're going to ignore the man behind the curtain here. All right, so I've got a little lemma here. So let A be B times Q plus R, okay? Basically, again, what that means is that's just doing division and rewriting it in the quotient remainder form. Okay, again, this kind of form is very important. Okay, so if I can have that, then the greatest common factor of AB is the greatest common factor of BR. Okay. So I'm going to first prove that, because then we're going to use that for something else. So let n be a common factor of both A and B. Okay. And so this will exist. It could be 1, for example. For example, like 8 and 9 don't have any common factors except 1, but that's 1. So we'll just let that be true. Then we can write, put this over here, A equals n times j, and B equals n times k. Okay, so there's a common factor. I can write each one of them as j times the other n times the other common factor, which I'm calling j in this case and k in this case. Okay, so since we have A is B times Q plus R, then R is A minus B times Q. Or R equals n times j minus n times k times q. Okay, so all I'm doing here is plugging in n times j into there, n times k into there, and there's a common k which I'm just going to factor out. Okay. So R has a factor n. Okay. And then let n be the largest common factor. Right. So that basically says that there's a common factor here. The biggest one I'm going to call n. It's also the same as that because it's got a common factor n. Okay. Good. All right, so we're going to use that to do what's called Euclid's algorithm. All right. So the first thing that we're going to do is we need to find the Q and the R, right, that basically satisfies this little lemma. And remember, again, all that means is it's the quotient and the remainder of A divided by B. Okay. So then what we're going to do is we're going to apply the lemma to say the greatest common factor between A and B is the greatest common factor between B and R. The thing that you'll see with some examples is, right, since the remainder, this remainder is always smaller than B is my divisor in this case, since R is smaller than B, right, this number, I mean, they'll be in order from A to B to R in terms of biggest to smallest. So these things get smaller, which is great, because that's basically the point of this. Okay, if we have a remainder of 0, then you found the greatest common factor. It's B, right? Else, we just repeat these steps. Okay, I'll walk through that again with a couple of examples. So these are the same two that we did in the previous video. So let's look at this, the greatest common factor between 180 and 144. So one thing is that I'm going to assume that when we do this, I've got A, B, A is bigger than B. If these are written the other way around, just flip it. There's a symmetry between, for a greatest common factor. Okay, so the first thing that we need to do again is do long division here. Okay. So 144, 6, 36. Okay. So then what we have is we say GCF of 180, 144, GCF, write this a little smaller so I can squeeze it all in, 180, 144, GCF, 144, that just slides over, and then the remainder. Okay. And then we do the same thing, 36, 144, 12 plus 2 is 144, 0. So GCF of 36, comma 0. And this answer is, sorry, this answer is 36. That was this step. Okay, so we did 2 steps of this. The first step was this one. The second step was that one, until I get a 0 there, and then I just write this down. Okay, so this was the same result that we got before. So the previous video, all we did is the first thing we did is write all the factors down. This was a little bit challenging for these two, just because they have a lot of factors. Each one of them has a lot of factors. The second way we did this is we did prime factorization, and if we found all the common factors from prime factorization and we combined those to get the same results. And this was using Euclid's algorithm. Okay, so notice this is a little bit more straightforward in terms of there's, I would say, an algorithm, which means a fairly clear step-by-step what you need to do. And the only maybe tricky thing in here is making sure you got the long division on this. Okay, let's do that other one that we did last time. Let me make sure I get the right numbers down. $33.15 and $135. Okay, so GCF 315, 135. Let me do I think 3 is too big, so 2, 7, 2, 1. And I just did 33 minus 26 in my head to get 6. Bring the 5 down. Let's see, 6. No, I think it's 4. I think it's going to be twice that. So 540, 57. Good. Okay, GCF on 135, 75. Okay, and notice here we very quickly brought these bigger numbers down. All right, so let me do 75. Whoops, 135 is 1, and 60. 60, 75, once, 15. Okay. So we can do one more step, but I am going to note that 60 is 4 times 15. And so since I got a multiple of that, not 4, but 15, right? So you can just pull that out automatically. So if you can see that at any stage, you can stop and just do that. Okay, so this I think was a lot easier than doing, first of all, trying to write all the factors down. Like once you get in anything into the hundreds, it's kind of a pain to do the GCF with just all factors. This one was a bit of a pain to do the prime factorization. It was a little tricky. There was some higher prime numbers in there that gave us a little bit of problem. So this is fairly straightforward, right? We may just need to, refine our long division skills, but we got that. Okay, so that wraps up the greatest common factor.